Good day, students. Welcome to mathgotserved.com. And this clip, we're going to be going over how to identify or test and evaluate functions. Okay, so the instructions for the first set of problems we're going to do is as follows. We are to determine if each relation represents a function. And then we're to explain our answers. So let's take a look at question number one. Let's say we have this relation right here. These are the set of input values or the domain, and these are the set of output values. Okay, we call this a relation because we're relating input values to output values, like 1 is related to 2, 3 to 5, 4 to 5, and 5 to 3. So is this relation a function? Remember, a function assigns every input to exactly one output, okay? So what we're going to do is focus on the inputs, okay? The inputs, or sometimes there'll be the x's or the domain. Focus on that and make sure that each input is going to exactly one output. So if you take a look at the four inputs we have here, 1 is going to 2 and 2 alone, 3 is going to 5 and 5 alone, 4 is going to 5 and 5 alone, 5 is going to 3 and 3 alone. So guess what? This relation is a function. All right, so let's explain our reasoning. The relation is a function because every input, basically 1, 3, 4, 5, is assigned or mapped to exactly one output. Okay, so that's what the definition of a function is. All right, let's take a look at number 2. So we have the inputs here, man, woman, boy, girl, and infants being mapped to numbers, okay? So the same question applies. Does this relation right here, does it represent a function or not? So what are we focusing on? We're focusing on the domain or inputs and making sure that they are assigned to exactly one output, okay? So another word for inputs, I didn't indicate that earlier, is domain. And then the output is a range. All right. Okay, so let's take a look. Man is assigned to exactly one output, which is excellent. Woman is assigned to two outputs, 23 and 14. Is that good or bad? That is bad. Okay, every input must be assigned to exactly one output. So what does that mean? The relation is not a function. Why is that? Because the input, woman, is assigned to more than one output, to more than one output. Okay, and that's the only pairing that causes this relation not to be a function, because boy goes to exactly one output, girl to exactly one, and infant to exactly one. Okay, so because of this situation right here, with women getting assigned to two outputs, this relation is not a function. Okay, let's take a look at question 3. Now, is this relation presented in tabular format? Is it a function or not? So what are we focusing on again? Remember, the rule is to focus on the x's or the inputs or the domain, okay? Now, when it's presented in numerical formats like this one, like the mapping format we had in problem 1 and 2, you want to focus on repetitions on the inputs, repetition on the x's, okay? When you have repetition on the x's and you have distinct y values, in that case, what you're having is a scenario where an input is assigned to more than one output, which is not a function, okay? So that's the quick way to deal with numerical representation of functions, okay? So for numerical representation, focus on repetitions on the x's input domain. Okay, that's the trick. All right, so let's take a look at this. 3, 4, 5, 6, they are all unique. There are no repetitions right here, which guarantees that each and every one of these will be assigned to one unique output, okay? So what does that mean? The relation is a function because, how do we know? There are no repetitions. There are no repetitions in the x's, which guarantees that every input is assigned to exactly one output. Okay, is assigned to exactly one output. So that's the shortcut for dealing with numerical representation of relations. Okay, now let's take a look at question number 4. We also have a tabular representation of a relation. We have the input-output table here, x's and the y's. So question, is this relation a function or not? So remember to focus on the x's and look for repetitions on the x's, okay? So what do we notice here? Take a look at -2. Do we have any repetitions? Yes, we do. You have -2 here and -2 there. That's no good. Well, why is that? Because of the repetition in the x's, we have a situation where -2 is being mapped to 7 and -2 is being mapped to 4. So what does that mean? That means that the same input is getting mapped to more than one output, and that is not a function, okay? So -2 is repeated, 2 is repeated. So that's the telltale sign, okay? So let's go ahead and write down our answer. The relation is not a function. Why? Because the input, -2, is mapped to more than one output. Okay, more than one output. That's a violation of the definition of what a function is. All right, let's take a look at question number 5. This is presented in ordered pairs. This is also a numerical representation of a relation. Okay, so is this relation that we have here a function or not? So remember, whenever a relation is presented in numerical format, we want to focus on the repetitions on the inputs for the x's. So let's look at 2, 3, 5, and 6. Any repetitions there? You have no repetitions. So that guarantees that every input will be mapped to exactly one output. Hence, this relation is in fact a function. Okay, so the relation the relation is a function. Because there are no repetitions in the x's, which does what? Which guarantees that every input is what? Every input is mapped or paired with is mapped with exactly one output. Okay, So this is in fact a function. Okay, let's take a look at question number 6. Now, in question 6, we're given the graphical representation of a relation. Okay, so is this a function or not? Is this graph the graph of a function or not? Now, this is the tip right here. When you're presented with a relation in graphical format, the graphical representation, what you use to test or determine if it's a function or not is something known as the vertical line test. Okay, remember your vertical line is an x equation. Okay, so when you run a vertical line across the entire domain of the graph, you're asking yourself, does it intersect at more than one point on the graph? If it does, what that means is basically that graph is assigning one input to more than one output. Okay, so that goes our vertical line right here. So what we're going to be doing is testing multiple x values graphically, okay? And then we're going to ask ourselves, is there any point in the domain of this function where this vertical line intersects the graph at more than one point? And what do we see here? Yes, it does. Okay, so at that point, the vertical line intersects right here and right here. It intersects more than once. So what does that mean? It means for this particular input value, you're going to have an output here and an output there. Okay, so this function, the graph of this relation, fails the vertical line test. So that makes it, it's not a function. Okay, so the relation graph is not a function. Why? Because it fails the vertical line test. Okay, that's sufficient to conclude that the graph of a relation is not a function. All right, now let's take a look at question number 7. This is a graph of a portion of a transformed quadratic function. So question is, does this relation, this graphical representation of a relation, does it represent a function or not? So we're going to use a vertical line test again because the relation is presented in graphical format. We're going to sweep our vertical line across the entire domain and see if it intersects the graph more than once at any point in time in the domain, okay? So let's do it. So we see starting from here, once. For the entire domain, this vertical line intersects the graph at exactly one point. So what does this mean? It means that this relation graphed here is the graph of a function. All right, so let's go ahead and write our answers down. The relation graphed is a function. Why? Because it passes the vertical line test. All right, let's go ahead and consider the next set of problems. The instructions are to determine if the given equation is a set of, is a representation of y as a function of x. Okay, all right, so let's take a look at the first number, number 8. What if we have x squared plus y equals 5? Now, is this a function or not? Now, this is a tip you want to keep in mind for identifying if an equation is a function, is a representation of y as a function of x. If y has an even exponent or absolute value bars, absolute value bars, guess what? Then it is not a function. It is not a function. Okay? All right. There are other conditions that can cause an equation not to be a function, but for the examples that we're going to be focusing on this course, this tip should suffice. Okay? All right. So let's take a look at this equation right here. What is the power of the y, the output function? It's odd. So what's the conclusion that we are going to arrive at here? The conclusion is this equation is a representation of y as a function of x, okay? So let's go ahead and write that down. The equation is a representation of y as a function of x. The question is why? Because y has an odd power. Y has an odd power of one. Okay, so that's the reason. All right, let's try another example. What if we have y squared is equal to x squared minus 1? Okay, so is this a function or not? Well, we'll look at the power of the output function or the range. So y is the output. The power is 2, which is even. So guess what that means? That means this is not a function, okay? The equation is not a representation of y as a function of x. Later on in this course, we're going to learn about how to graph relations like this. These are known as conic sections, okay? If we graph it, we're going to end up with something called a hyperbola, okay? And that is not a function because it's going to fail the vertical line test. But just focusing on the power of the output function, that automatically helps us to see that this is not a function, okay? So let's write down the reason here, because y has an even power. And also another way to do this, if you want to do it algebraically, is you can take the square root of both sides. Let's go ahead and do that real quick. Take the square root of both sides. Because of you have a square root of a square here, you're going to end up with y equals plus or minus to square root of x squared minus 1. So you see this right here? That is going to cause a specific input value to have two output values, evaluation of the definition of a function. Okay, so that's just another way to show that it's not a function other than graphing it. All right, let's take a look at another example. What if we have x equals the absolute value of y plus 5? Now, is this this equation, a representation of y as a function of x? And the answer is no. Okay, why not? We have the absolute value function on the output function. Okay, and that's going to create an input value getting mapped to two output values, because if we take out this absolute value bars, we're going to have plus or minus y. Okay, generating two distinct output values for one specific input value. So answer, the equation is not a representation of y as a function of x. Because of what? Because y, the output value, has absolute value bars. Okay, absolute value bars. That's an automatic disqualification. Okay, now what if we have the scenario x equals 4? What's the power of y here. Y has no power. Okay, it's not present. So we can't really categorize the power of y as odd or even. So what can we do to figure this out? Well, we have to carry out we have to use another representation of this equation. Can we graph the equation can we graph x equals 4? Can we plot the graph of the equation x equals 4? And the answer is yes, absolutely. We can plot the graph of that function. So what we're going to do is we're going to make a change in representation and use an alternate representation to arrive at the desired result, okay? So the graph of x equals 4 is simply a vertical line that has an x-intercept of 4, okay? So that's what the graph looks like. So let's say this is our y-axis right here. There goes your x-axis. That's a value 4. Now, this line is the line with the equation x equals 4. Now, what did we say earlier concerning testing if the graph of a relation is a function or not? We said that the best tool to use is the vertical line test. So that's what we're going to apply again, okay? All right, so this is the vertical line we're going to be using to carry out the test. And we recall what the vertical line test is. If we have a vertical line that intersects the graph of a relation at more than one point, then that relation is not the graph of a function, okay? So if we place the vertical line on the graph of the equation x equals 4, how many points of intersection are there? You find out that there are infinitely many points of intersection. This line and this vertical line intersect at every point, okay? So since we have more than one point of intersection between the vertical line and the graph of the relation x equals 4, what's the conclusion? This graph is not the graph of a function. Hence, this equation does not represent y as a function of x, okay? So let's go ahead and write down our answer. The equation does not represent y as a function of x. Why is that? Because the graph of the equation, fails the vertical line test. All right? Line test. All right, let's take a look at question number 12. What if we have the function y equals the absolute value of x plus 5? Now, does this equation represent y as a function of x? Now, we notice that y has an odd power, which is excellent, and y does not have absolute value bars around it. Okay, so guess what? This equation actually represents y as a function of x, okay? So even if you think about the graph of this function, let's just consider that real quick. If you have your absolute value function plus 5 is just an absolute value function that's shifted 5 units up. And if you apply your vertical line test to the graph of this function, you notice that it's going to pass the vertical line test, okay? So if we just look at the symmetry of the exponent of y and the presence or absence of absolute value bars, we can easily tell that this is an equation that represents y as a function of x, all right? So the equation represents y as a function of x because how do we know? Y has an odd power, and odd power with no absolute value bars, okay, with no absolute value bars. All right, so that's just an easy way to algebraically determine if the equation is that of a function y as a function of x or not. You can also use the graph also and say the graph passes the vertical line test. That will also be a good conclusion. Okay, so the next group of problems, we're going to be evaluating functions that specified input values. All right, so for question number 13, let's say we have the function f of x equals 3x plus 5. Okay, a part, let's say we are to find what f of negative 2 is. So what is f of negative 2? F of negative 2 is basically what you get when you input negative 2 in place of x in this function. Okay, so you're going to have 3 times negative 2 plus 5. After making your substitution, you just use the order of operations to simplify your arithmetic expression if that's the case, which is the case here. Okay, so you multiply, you get negative 6 plus 5. Your final answer is negative 1. Okay, B, what if we have f of 3? So we substitute 3 into this function in place of x, and then we have 3 times 3 plus 5. Okay, 3 times 3 is 9 plus 5. 9 plus 5 is 14. That's the output when the input is 3. Now, what if we have an algebraic expression for the inputs? Let's say x minus 1. Now, how do we do this? We have 3 multiplied by the input plus 5. So we're going to write this as 3 times the input, which is x minus 1, an algebraic input this time, plus 5. All right? So now let's go ahead and distribute first. Distribute 3 across these two terms. So we have 3x minus 3 plus 5. And then we can combine like terms. 3x, negative 3 plus 5 is positive 2. So 3x plus 2 is our final answer. All right, let's take a look at question 14. What if we have a radical function? Okay, so let's say f of t is equal to the square root of t plus 4 minus 3. All right, so for the a part, we're to find what f of negative 4 is. So how do we figure this out? We'll simply input negative 4 for wherever t is in this expression to the right. So we have the square root of negative 4 plus 4, square root of that minus 3. Okay, so negative 4 plus 4 is 0, so we have the square root of 0 minus 3. And 0 minus 3, final answer is negative 3. Okay, B part. What if we were to find out what f of 5 is? Okay, f of 5. So f of 5 is going to be the square root of 5 plus 4 minus 3. All right, using order of operations, simplify what's in the radicand first. 5 plus 4 is 9, so the square root of 9 minus 3. Square root of 9 is 3, so we have 3 minus 3. Your final output is 0. All right, for the C part, what if we were to find what f of 4 t square is? F of 4 t square. Okay, so what is this going to be? Well, we're just going to plug in 4t squared in place of t, so we have the square root of, actually, let's do this. Let's make a slight change to the problem. So 4t squared minus 4. Okay, this is more like it. All right, so we want to do f of 4t squared minus 4. So for this one, we're going to plug in 4t squared minus 4 for t in the function. So we have the square root of, instead of t plus 4, we're going to take out t and replace it with 4t squared minus 4. plus 4, okay? And then that's minus 3. So we're going to focus our energy on the radicand, simplify that completely first, and then see if we can simplify the resulting expression when we reduce what's in the radical, okay? All right, so let's go ahead and do that. So we have the square root of 4t squared minus 4 plus 4 minus 3. So minus 4 plus 4 add up to 0, okay? And then we have the square root of 4t squared minus 3. All right, here we're going to be rooting 4 and t squared, right? If we do that, we end up with 2t minus 3. Okay, and that goes our final answer. If you square root 4, you get 2. If you square root t squared, you end up with t. All right, let's take a look at problem number 15. For problem 15, we're going to be dealing with a piecewise defined function. So let's say f of x is equal to 2x plus 1 when x is less than 0, and it's x minus 3 when x is greater than or equal to 0. Okay? All right. So for the a part, what if we were to find f of negative 1? So one thing to help you with this problem is to give yourself a visual as to what's going on, all right? So if this is the number line, if you're anywhere to the left of 0, so let's say this is 0 right here, anything to the left of 0, you're going to have the first function, okay? So let's say this is function 1 right here. So anything to the left of 0 goes right here, okay? But if you have 0 and anything greater, guess what? You are going to be looking at the second function, okay? Because it says greater than or equal to 0. So for the second function, you are going to be residing in this interval right here. Now let's take a look at the a part, f of negative 1. Where is negative 1? It's to the left of 0 right here. So we're going to be using the first function. So it's going to be 2 parentheses negative 1 plus 1. All right, that is equal to negative 2 plus 1, which is equal to negative 1. There goes your first answer. Now how about if you want to do f of 0? If you're on 0, because the second equation has the inclusion bar here, that means that when we're evaluating the function, that's where the discontinuity happens, we're going to be using the second function, okay? So it's going to be 0 minus 3, which is equal to negative 3. Part C. What if we were to find f of 2? 2 is clearly greater than or equal to 0, so we're going to be using the second function again. Input 2 into the second function, 2 minus 3. Your final answer is negative 1, and there goes your output. Thanks so much for taking the time to watch this presentation. If you found the contents of this tutorial helpful in your study of relations of functions, do give us a thumbs up. Your positive feedback is very valuable and supportive to us. If you have any questions or comments, just place it in the comment section below, and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.